You've probably heard that lactic acid causes muscle burn during exercise. That's actually wrong. And if you don't understand what's really happening in your muscles right now, you're missing the one thing that determines whether you can sprint for 10 seconds or jog for an hour. Here's the problem most beginners face: you think energy systems are complicated chemistry. They're not. They're three simple pathways your body uses to power movement. By the end of this video, you'll know exactly which system kicks in when you move, why you get tired, and how your body decides between sprinting and endurance. I'm going to show you what actually limits your performance. Not theories. Evidence from recent exercise science that changes how you should think about training. The currency your muscles actually spend every muscle contraction you make costs energy. Not calories. Not carbs. ATP. Adenosine triphosphate. It's the only energy currency your muscle cells accept. Think of ATP like cash in your pocket. You need it immediately to move. The problem? You only store about enough for 3 seconds of maximum effort. If you only have 3 seconds of ATP stored, how does your body keep moving for minutes or hours without running out? Your body solves this with 3 different energy systems. They all make ATP, but they work at different speeds and last different amounts of time. The phosphagen system is your emergency fund. The glycolytic system is your credit card. The aerobic system is your salary. Each one kicks in based on how intense your movement is and how long you need to sustain it. A 2010 review by Baker and colleagues in the Journal of Nutrition and Metabolism found that high-intensity exercise can increase ATP demand up to 1,000-fold compared to rest. Your muscles need to regenerate ATP at exactly the rate you're using it, or you stop moving. Most beginners think aerobic means with oxygen and anaerobic means without oxygen. That's incomplete. The truth about these labels will surprise you, and it changes everything about how you train. We'll resolve that in Section 4. System 1, the phosphagen system. The phosphagen system is pure speed. No oxygen needed. No waste products. Just instant energy. Here's how it works. You have a compound called phosphocreatine stored in your muscles. When you contract a muscle, an enzyme called creatine kinase breaks down phosphocreatine and uses it to instantly regenerate ATP from ADP. This happens in milliseconds. The advantage? Maximum power output. A 2024 study by Arkitsky and team in Peerage showed that during 15-second sprints, athletes rely heavily on the phosphagen system for explosive efforts. It's why you can jump, throw a punch, or accelerate in a sprint. The limitation? Capacity. You only have enough phosphocreatine for about 10 to 15 seconds of all-out effort. After that, the stores are depleted. Your phosphocreatine recovers incredibly fast after you stop moving, which is why rest intervals matter more than you think. Research shows half of your phosphocreatine regenerates in just 30 seconds. This is why sprinters rest between sets. They're literally waiting for their energy stores to reload. The phosphagen system powers your first seconds of any movement. Vertical jumps. Powerlifts. Starting a sprint. But the moment you sustain effort beyond 10 seconds, your body shifts gears. System 2, the glycolytic system. When phosphocreatine runs low, your body switches to glycolysis. This system breaks down glucose or stored glycogen without needing oxygen. It produces ATP faster than the aerobic system but slower than phosphocreatine. Here's the process simplified. Glucose gets broken down into pyruvate through a series of chemical reactions. This produces small amounts of ATP. When you're working hard and oxygen availability is limited, pyruvate converts to lactate. This regenerates a molecule called NAD+ so glycolysis can continue producing energy. Now here's where the myth comes in. For decades, people believe lactate causes muscle fatigue and that burning feeling during hard exercise. A 2024 review by Postiglione and colleagues in the journal Cells found something different. Lactate doesn't directly cause fatigue. In fact, when researchers bathed isolated muscle in lactate at concentrations you'd see after a 400-meter run, force production didn't drop. So what does cause fatigue? The real culprit isn't lactic acid, and understanding this will change how you recover between hard efforts. We'll resolve this soon. The glycolytic system can sustain high-intensity efforts for roughly 30 seconds to 2 minutes. Think 400-meter sprints or a hard set of resistance training. A 2012 study by Ardioli and team in the Journal of Visualized Experiments confirmed that the glycolytic system contributes around 50% of energy during a standard 30-second Wingate test. But there's a cost. Glycolysis produces hydrogen ions, which lower muscle pH and contribute to that burning sensation. Your body can buffer some of this, but eventually you have to slow down or stop. Why this matters now? Let's pause here. You now understand 2 of the 3 systems. You know phosphocreatine powers your first explosive seconds. You know glycolysis takes over for high-intensity efforts up to about 2 minutes. But remember the first question? You only store 3 seconds of ATP. So far we've explained maybe 2 minutes of movement. What happens when you need to exercise for 5 minutes, 30 minutes, or hours? That's where the third system completely changes the game. And this is the system most people misunderstand. Stick with me, because once you see how all 3 systems work together, you'll finally understand why your body feels different during a sprint versus a jog. System 3, the aerobic system. The aerobic system is your endurance engine. It uses oxygen to completely break down carbohydrates and fats in your mitochondria, producing large amounts of ATP. Here's the process. Pyruvate from glycolysis enters the mitochondria. It goes through the Krebs cycle and electron transport chain, where oxygen acts as the final electron acceptor. This produces far more ATP per molecule of glucose than glycolysis alone. Around 30 to 32 ATP molecules compared to just 2 from glycolysis. The advantage? Massive capacity. As long as you have fuel and oxygen, the aerobic system can produce ATP for hours. A 2021 review by Hargreaves and Spreet in Nature Metabolism confirmed that for most endurance events, the aerobic system is the primary energy source. The limitation? Speed. The aerobic system cannot produce ATP as quickly as the phosphagen or glycolytic systems. This is why you can't sprint at maximum speed for a marathon. The demand exceeds what aerobic metabolism can supply. Now let's resolve the second part from earlier. You were told aerobic and anaerobic describe whether oxygen is present. That's misleading. Baker's 2010 review clarified this. The entire glycolytic pathway is technically anaerobic. It doesn't require oxygen whether you're sprinting or jogging. What changes is what happens to the pyruvate afterward. During low-intensity exercise, pyruvate enters the mitochondria for aerobic metabolism. During high-intensity exercise, it converts to lactate to keep glycolysis running. Same pathway, different endpoint. The labels aerobic and anaerobic describe the overall energy contribution, not the chemistry of glycolysis itself. When each system dominates, here's the practical part. All 3 systems are always active. They don't turn on and off. What changes is their relative contribution based on intensity and duration. A 2001 review by Gaston in Sports Medicine showed that during maximal efforts lasting around 75 seconds, aerobic and anaerobic systems contribute roughly equal amounts of energy. That's earlier than most people think. For a 100-meter sprint lasting 10 seconds, roughly 90% phosphagen and glycolytic, 10% aerobic. For an 800-meter run lasting about 2 minutes, roughly 40% anaerobic, 60% aerobic. For a marathon? Over 95% aerobic. Now let's resolve that fourth question. You wanted to know what really causes fatigue if it's not lactic acid. A 2002 review by Nielsen in the journal Physiology found the primary culprit is inorganic phosphate. When phosphocreatine breaks down, it releases creatine and inorganic phosphate. As phosphate accumulates, it interferes with muscle contraction at the cellular level. In high-intensity efforts, phosphate buildup reduces force production. In longer efforts, glycogen depletion and changes in calcium handling also contribute. Lactate? It's actually protective in some cases. It can be converted back to glucose in the liver or used as fuel by other muscles. This is why recovery strategies focus on restoring phosphocreatine, clearing metabolites, and replenishing glycogen. Not flushing lactic acid. Bringing it all together, let's resolve back to the third question now. Phosphocreatine recovery happens fast because it's powered by aerobic metabolism during rest. A 2008 study by Forbes and team in the European Journal of Applied Physiology showed that after high-intensity exercise, phosphocreatine can recover in under a minute if you're completely resting. This is why interval training works. Short bursts deplete phosphocreatine. Brief rest restores it. Repeat. And the first question? Your body keeps moving beyond 3 seconds because these three systems overlap and complement each other. The phosphagen system buys time for glycolysis to ramp up. Glycolysis buys time for aerobic metabolism to meet demand. It's a cascade, not a sequence. Understanding this changes how you train. If you want explosive power, train the phosphagen system with short, maximal efforts and full recovery. If you want sustained high-intensity capacity, train the glycolytic system with intervals of 30 seconds to 2 minutes. If you want endurance, train the aerobic system with longer, lower-intensity work. The systems don't work in isolation. They work in coordination. And your training should reflect that. Conclusion: you came here thinking energy systems were complicated. Now you know there are 3 simple pathways that power every movement you make. ATP is the currency. Phosphocreatine is your instant energy. Glycolysis bridges the gap. Aerobic metabolism sustains you. The biggest takeaway? Fatigue isn't caused by lactic acid. It's caused by phosphate accumulation and fuel depletion. Recovery isn't about flushing waste. It's about restoring energy stores. If you want to train smarter, understand which system you are targeting and give it the right stimulus. That's how you get faster, stronger, and build real endurance. If you want more science-based content, make sure to like and subscribe.